That's just part of the unit cell, huge thing. So here's this nanosphere, and it's connected to a giant nanodonut or nanoring. And very interesting point group symmetries. And they're together. Achim called these a little later Keplerites after Johannes Kepler, famous scientist who didn't do a lot of chemistry. He's mostly an astronomer, mathematician, really. There's the formula of this monster. So the yellow part is that guy, and the blue part is the nanoring. Again, I don't know what they're good for, but that shouldn't be the only criteria, right? So I've borrowed a slide from Lee Cronin, who was mentioned by Chaumont as an extraordinarily productive and creative young guy. And this is Lee's slide, as I've noted. And it's simply showing some of the building blocks as they get larger and larger and larger. And I think this is still the current largest POM, which is called the blue onion, or the blue lemon, because it's shaped like a lemon. Here are the nanorings, and they come in different sizes. One nice thing, there's many beautiful aspects of this chemistry, other than they're gorgeous and they go on covers of journals. If you look at the motif like of the Keplerate, the nanocapsule, you've got these interesting pentagonal coordinating units. They're interesting because they're slightly bent. Let's go back to the previous slide and look at this. So here's this unit. It's got a metal oxo in the middle, but trans to the oxo is not another oxo. It's usually an aqua. So this bond is short and strong, and that one's long and weak. So what that does is it pulls the central metal out. But what that does is it makes this 6-atom unit bent. It's a little bit of an eggshell. And when you put the bits of eggshell together, you get an egg. At least the whole eggshell. And the reason that this is out is an electronic one that we can discuss in detail later on. It's a very important aspect of many types of science, including metal oxide surfaces, which have myriad applications. So you put those together, you get a sphere. So that you can connect them in different ways. So right now, these units in blue are connected with one single atom, which is vanadium VO6. You can connect them with other things that are much larger. And that's what's shown here on Lee's slide. Here's an example where you're not connecting these nonlinear units, these concurved units with just an atom, but you're connecting with larger units. And so you can see the diversity that can be developed in this chemistry. Now, I kind of want to touch on POM characterizations very quickly. Then we can go into much more detail and up to 20 different techniques, as you guys are interested in. And we also have some other interesting speakers whose presentations I look forward to. So here's the so-called lacunary. You take the parent compound called plenary, and you treat it with molybdates, tungstates, and vanidates. Base will hydrolyze it, meaning remove one or more metals. And when you remove one metal, the tungsten tungsten oxygen, 4+, you're left with this. So these oxygens here have a higher negative charge because you've removed this highly positive unit. And you go from the Kagan parent, where all the metals in gray are the same by symmetry. So you have singlet NMR, tungsten NMR. You go to that, which has CS symmetry. So you have 6 different kinds of metals when you put the mirror plane through it. And there are the chemical shifts. I love this slide because it shows how incredibly high resolution sub-NMR nuclei can be without it being fancy. There's powerful 2D methods that we can all use today, and they're wonderful. If there's interest in that, we can talk about that some more. But NMR is just very powerful for characterizing POMs. Basically every atom in the POM you can characterize, almost every POM. So the central atom in the Kagan series is the metal, in this case tungsten 183 NMR. There's molybdenum 9597 NMR, but that's a bad NMR nucleus. Vanadium 51 in polyvanidates is very good for several reasons. And again, if there's interest, we can go into more detail. But I think there may be an NMR talk, right, John? No? Okay, so I covered. Okay, so here's an FTIR. So vibrational spectroscopy is also pretty informative. It's kind of like organic and small biological molecules. So you have higher frequency areas where the frequencies are more reproducible. And then you have kind of lower energy, lower frequency areas that are the so-called fingerprint. And each particular POM has an ensemble of peaks that are characteristic of that structure. And ramen is increasingly useful. It's just not as available, and there's a number of issues. But we're increasingly using ramen, particularly confocal ramen, which is more sensitive. We're going to have a talk on ramen, I believe, right? And ramen was developed here in India, right, by Shamskar Raman. Okay, so there's you can characterize POMs by microscopies, including the scanning force microscopies, the main one being scanning tunneling microscopy, STM. So you can see individual molecules. And it's surprising how often these will crystallize on a surface very nicely. So these are Kagans. Kagan is a sphere, so they're spherical. The Wells-Dawsons are an American football shape, so that's what you see. And the nice thing about this is that you can, again, the POMs have high charges, so you can change the cation. You can have a small cation like sodium. It'll probably be hydrated, so sodium with 5, 6, or 7 waters. And you can go to something really humongous, big, like tetra and heptylammonium, nitrogen with 4 heptyl groups on it. And what will happen is that these corrugations, these spacings will go out as the cations push out the anions. And you can, there's some reversibility to this. Okay, so the STM and scanning probe microscopies are not generally as useful as regular EM, transmission, electron microscopy, and TEM and SEM. The good thing about those is we have EDX coupled with SEM and TDX, so we can do elemental analyses now on surfaces that might have POMs and other things. This is a paper that we did back in 2002. Then electrochemical methods are very powerful for almost any POM. We'll talk some more about why certain POMs reduce and others don't, at least not as well. So in voltammetry experiment, we just measure the current, we actually scan the potential on the working electrode. So there's the current. So if you start here and you scan in the negative direction, you're reducing it. So you have one reduction, another reduction, a third reduction, a fourth reduction. So what this is showing is that it's this compound. So iron reduces fairly easily, iron 3+ to iron 2+. But as you get down negative enough, you put electrons into the tungstate units, the WO6 units. And when you put tungstates in electrons into the tungstate, they're very delocalized, which gives rise to some intense absorptions called heteropolyglues, because they're blue. And I never thought that these were interesting other than intellectually. They're wonderfully provocative. But recently it's been found that you can use low energy light to stimulate those delocalized electrons to do things. And those may have applications in, for example, infrared solar fuel production. There's many other techniques. We've used many. Chronoamperometry is following current amperes with time. And that's powerful because it can give you information about size of a molecule, because it gives you the diffusion coefficient. And if you have that, then you can get, as we'll see in a later lecture, you can get the size. So you can actually get the size of POMs, and you can see how the size changes as you change the counterions. This guy's 6-, so there's 6 sodiums, for example. And that's going to change if you have another ion, like tetrabutammonium, TDA, very popular. So this is just a slide of the techniques we've used. It's not a complete list. I'm not going to go through all this. There's not time. I just want to give you an overview. And I want to set up any discussion that any of you might have. I know we're going to have some talks on some of these techniques. But I'd be delighted to go into a lot of detail in all of these as is interest. So for soluble species, there's obviously NMR. It's hard to beat for being informative. FTIR Raman, resonance Raman, and confocal Raman. Optical spectroscopy. There's all these electrochemical methods. There's different mass specs. Lee Cronin has pioneered the use of one of these to characterize POMs. For solids, there's all those quite known techniques that apply well for POMs: X-ray, both single crystal XRD, X-ray diffraction, powder X-ray diffraction. There's solid-state NMR, more involved. There's SEM, quickly with EDS, EDX now, where you can do elemental analysis on a particular spot you're seeing in the electron micrograph. Transmission electron and TEM, EDX as well, and then thermal methods. Thermogravimetric analysis and differential scanning calorimetry. So these are methods that TGA is weight loss as you heat a sample up, and DSC is change in heat flow as you heat a sample up. And that can give you some insight, not just about stability, but also about composition. Okay, then there's techniques that are kind of nanoscale, scanning tunneling, I've noted, atomic force microscopy. Small angle X-ray scattering is becoming increasingly useful. Small angle neutron scattering is very useful, but there aren't many places you can do it. I'm sure there's some in India, but it's just hard. It's not a routine technique. You need to go to a linear accelerator center, a neutron source. And then techniques. POs do a lot of wonderful things. Just all kinds of catalysis is one. If you want to study a mechanism, a catalytic mechanism, you've got to do kinetics essentially. So ideally you want methods where you can follow the change in concentration with time. That's what kinetics is. Concentration, y-axis, time, x-axis. Things change. Concentrations change. And the single most powerful method for very fast reactions these days is transient absorption spectroscopy, TAS. So we're using that in photoelectrodes, for example, of various kinds, including ones with POMs. And I can talk about that if there's interest and so on. Okay, so I mentioned medical applications. I'm just going to note this slide. So there's, POMs are very potent antiviral agents. Okay, they haven't been approved for use because they're very unusual. The drug development world in the United States anyway has very high barriers, and it's the Food and Drug Administration, FDA, you might have heard of that. So the barrier to get through FDA approval is high. And and it's all geared toward low molecular weight organic molecules and peptides. Nobody has any idea what a POM is. So we have great results with all kinds of viruses from HIV, HSV, RSV, HPV, all the way to Ebola. POMs are very potent inhibitors. But nobody knows what they are. And we realized that we were up against a lot if we were going to try to get these approved. So we basically moved our interest in research to another area. Now they're getting very interesting again because we have a new type of POM that's a catalytic anti-cancer agent. I haven't published it, I haven't discussed it, I'm not sure I'll mention it here, but we have, and I'll report it soon. And it's very interesting. So we have a startup company on that. Again, if there's the startup companies, we can talk about that. Now, I'm just going to show a slide here that summarizes a lot of catalytic science. You can do it with different kinds of molecules, but it's hard to beat POMs. So POMs are usually in the oxidized form, and you can tune them because they're so easy to synthesize and make different derivatives, different isomers. And you can use a POM to oxidize many different substrates, like the lignin out of biomass, as I mentioned, biological targets for medical use, toxins, chemical warfare agents, environmental toxins. We have a lot going on in that area. And then if you have the excited state, you pull off CH bonds and do all kinds of chemistry. And we developed all of that about 20 years ago in 31 papers, many in JACS. And I haven't been working in the area for a while, but others have. And I think there's a lot there that we didn't do. And that was kind of before we had time resolved spectroscopy on the femtosecond time scale. So when you oxidize any of these things, you decontaminate it, you transform it. At the same time, the electron goes to the POM, and you get a blue color. Because the delocalized electrons give you transitions that are complementary to blues. It's very intense. So that can be used as a detector system. My laser pointer's dying. I'm going to go to red. Yours? Can you see that okay? Oops. I don't want to do that. Okay, so when you oxidize anything, you can actually detect it by a color change, just like this. And then another beauty is that if you use the right POM, it'll react with air, and you'll reoxidize it and generate water. So you have a way to do green chemistry with air. So we use that in many aspects. Here's one that got a lot of attention. We published it in Nature in 2001. It's covered in many magazines, including Chemical and Engineering News. So this is a copyright from the C&E News article. But it's the same two steps shown here. But it's a little fancier than that, and it has some new ideas in it. Let me get the right laser. So, okay. So we made this by the thermodynamic synthesis, as I mentioned. So that gave us an equilibrating POM ensemble, all these POMs. So this POM here is the main one. That's about 90%. And that had just the right potential to oxidize the lignin in wood and leave the cellulose. So lignin, when you take an electron out, dissolves. So you get soluble lignin. You can filter it off, and you're left with cellulose for the global markets. But what do you do with the lignin? Okay, so the POM gets reduced. Lignin dissolves, left cellulose. But what you can do is you add air, and that will reoxidize the POM and make water. But it'll also do something else. This ensemble, if you heat it up enough, will mineralize all this organic stuff, convert it into CO2 and water. So you basically have a way to use air to get the cellulose out of paper with no pollution. And that's what this says. So this was pioneering in many ways. It was a self-repairing catalytic system. It was one that was also buffering itself. And the whole thing's tunable. Yeah, so typical in many cases in my career, I didn't follow it up with other papers, but put it out there, and that was that. Okay, I want to finish up now. How am I doing on time? Okay, not a lot. There's the whole area of covalent organic or biological modification of POMs. So POMs, it's very easy to put organic and biological groups on it. One example, one example is esterification. So you can think of a protonated oxygen between two metals as inorganic carboxylic acid. So if you have a carboxylic acid and alcohol, you get an ester in water. Now it turns out if the POM is vanadium, so M is vanadium, the ester is incredibly stable. You can boil it in water and it will not hydrolyze. And to me that's remarkable. You know, think about sodium methoxide or potassium t-butoxide. These are very sensitive to water. They're alkoxides too. So is that you can boil it in water for a week and it stays there. So that gave me a lot of ideas about things we might use, particularly in biomarking medicine and catalysis. The other thing, again, is that POMs are models of metal oxides. So metal oxide surfaces can be esterified as well, but they're incredibly hard to study. Again, how do you do NMR on an ethyl group on a metal oxide surface? So that you can think of this as an equilibrium process. In the case, the K value is really big for when M is vanadium. It's not so big for molybdenum or tungsten. Okay, so we have a way to put organic groups on POMs. This is just an example of how we took that and made kind of MOF-like structures, molecular porous structures, where now we have POMs as redox-active catalytic structural components. So this is just a V6 unit, and this is a triester starting with tris hydroxymethyl compounds. There's an amide, and it ends with a carboxylic acid. So this is just that, ending with two carboxylic acids, and you throw in a lanthanum, and you get this crystallizing out, one step. And this is a while ago, almost 10 years ago now. And it does a lot of things. Again, we didn't really exploit it like we should have. So it's kind of an unusual sort of MOF. And this is another example. If you take this, sorry about that, hopefully by the end of the week I'll know how to use this thing. Okay, so if you take this trial, you can boil this up with many vanadates, including V10, POM of 10 vanadiums, and you get a very interesting material where the V10 has been converted to V6, the red balls are vanadium, bridged by oxygen. And this is, we've made a whole group of these. These are polymers that swell extremely rapidly when exposed to various things. That's interesting because one of the challenges in material science is design materials that are physically responsive to something, like an air pollutant. Okay, we're all breathing some formaldehyde in here, not very much, but formaldehyde's not good, it's carcinogenic. So it'd be nice if you had a jelly material that would take up formaldehyde, trap it, and then ideally detect it by oxidizing it, reducing the POM, the color change, and catalytically removing it. So that's what it does. So I kind of refer to this as a nanofactory. We thought that was initially the structure. Now we have refined it using solid state, carbon NMR, and so on. It's a little bit more complicated. Here's showing the material actually swelling. This is the same material, this nanonet, with linked V6 units. And as a powder, it's there. You can add a number of things. They could, in this case, just DMF, the organic solvent. But you can also swell it with pollutants. So it's a way to trap and do chemistry and remove pollutants. Here's one example. Thiols, SH and air being removed. The thiols are the smelliest compounds in human environments. If there's a way to remove it using air, that would be great. Huge market. So these things do that. This is 9,000 turnovers at room temperature using room air. So this is under review right now. Let me finish up with solar fuels, just some aspects of this. So it's the list of, I've got to get my handle on this. So there's a list of the 10 challenges facing mankind for Rich Molley, but most people agree. He passed away a few years ago. He won the Nobel Prize for fluorines. Energy is really at the top of the list for a number of reasons. One is we're running out of fuel, but the bigger issue the last 3 or 4 years with incredibly rapidly changing climate is the environment. Every indicator that we have, not just the amount of CO2, which is now 400 parts per million from burning fossil fuel, but many others, are